Okay, so we're going to now do the Otto cycle question in this chapter. We've already done one in a previous video, but we're going to do this one as well. So an engine with a compression ratio of 9 is running on an air standard Otto cycle. Prior to the compression process, modeled by a polytropic process with n equals k equals 1.4, the air is at 100 kilopascals, 32 degrees Celsius, and 600 centimeters cubed. The temperature at the end of the polytropic expansion process is 800 Kelvin. Determine the highest temperature and pressure in the cycle, the amount of heat transferred in kilojoules, and the thermal efficiency. Assume constant specific heat values at room temperature. So in this question, we're told there's something that we're modeled by a polytropic process with n equals k equals 1.4. And we spoke a bit about what that means in the first Otto cycle video. But just as a reminder, what that means is that this is an isentropic process. So whenever we have a polytropic process where n happens to be k, where k is the ratio of Cp over Cv, whenever we have that exponent being equal to k, which for air is 1.4, we know that the process is isentropic. But again, treating it like a polytropic process with 1.4 is also perfectly valid. All right, so let's get started then. Okay, so I'm just going to draw out the cycle. So we're going to start at state 1. Sorry, like this. So we have pressure and specific volume. We go from state 1, which is, let me draw it a little further over the side. State 1, so the gas is just sitting there in the cylinder. We then reduce the specific volume a lot by compressing it, right? And this is, of course, the compression. So the piston is moving up and squeezing the fluid inside. And of course, the pressure goes up as the specific volume goes down. So this is sort of curved upwards and to the left. This we said is isentropic, or if you want to call it polytropic with n equals k, that's fine too. Now the next step is, of course, we add heat to the system. So we're going from 2 to 3. Now remember, when we add heat, this is an isochoric process, which is why we have a vertical line here. So we've already done the compression. In this step, the piston is not moving. The volume that we have is constant from 2 to 3. And I'll just put a little Q in over here. And then we're going to do the exact opposite of a compression. We're going to expand, and this is where our work gets done. Now, as we expand, it's with the same compression ratio, or rather the inverse compression ratio. We're going to go from state 3 to 4. So that means that if before our specific volume shrunk by a factor of 9, here it's about to increase by a factor of 9. Now, of course, when we decreased our specific volume in the compression process, the pressure went up. And when we decreased it, the pressure is going down slightly. So that's curving down and to the right. And then, of course, we have the heat rejection, which also occurs isochorically. So in a real engine, this is like the exhaust. Now, we can get started with this problem now. So we're told we're starting at state 1. State 1 being 100 kilopascals and 305 Kelvin. And we're asked to find the highest temperature and pressure at any point in the cycle. So we can already know at least where that happens, right? In any Otto cycle, you're going to have the highest temperature and the highest pressure right before the expansion. So at state 3 is what we're talking about. And that also goes for Rankine cycles and for Brayton cycles as well. So we have a very highest temperature, highest pressure at state 3. So let's figure out what that is. So since this is an isentropic process, we can use the isentropic relations. So again, another reminder, the isentropic relations are basically the polytropic relations. They're the same thing, but specifically we're going to be using K instead of N because as an isentropic process, our N is really K. So we can use the following expression. T2 over T1 equals, all right, volume 1 over volume 2. And, well, rather, this we can express as T2, which we're trying to find. So we need to work our way to state 3 via state 2. So we need to go find state 2 first. Sorry, there's an exponent here, K minus 1. So T2 equals T1 times V1 over V2 to the K minus 1. Now V1 over V2 is very much the compression ratio because the volume at 1 before the compression is 9 times greater than the volume at 2. So we can say that T2 equals T1, which is 305 Kelvin always we're using, times 9 to the K minus 1. And for air, K is 1.4. And if you calculate this, you'll get a value of 734.5 Kelvin. This is the temperature at state 2. Now we can also find the pressure at state 2. Now the pressure at state 2 is, we're going to use the ideal gas law. So we're going to say that P1 1 over T1 equals P2 V2 over T2. And what do we know here? Well, actually, we don't know V1 or V2 individually, but if we can express them as a ratio, well, then that's, again, the compression ratio, and that's good. We know T1, we know T2, because we just found it, and P1 was given in the question as 100 kilopascals. So if we rearrange this, we can express P2 as V1 over V2 times T2 over T1 times P1. And okay, so putting in the values, like we said, V1 over V2, we know the ratio, it's 9. T2 over T1, well, we know T2 we just found was 734.5, that's this guy here, divided by T1, which is given, is 305. And P1 is also given as 100 kilopascals. So our answer will be in kilopascals, and if you calculate this out, you get 2167 kilopascals, or 2.167 megapascals. So this is the pressure at state 2. So now we know state 2, we can maybe work our way towards state 3 a little bit. So the thing is, we can use this same relation to go from 2 to 3 and find the pressure. Of course, though, we'll need to know the temperature ratio T3 over T2, and we don't know T3. But if you read the question, you'll see that they give us the temperature at state 4. So if we know the temperature at state 4, which is after the expansion process, and we know the compression ratio, we can pretty much use a similar equation to this one over here and work our way backwards from 4 to find the temperature at 3. And that's what we're going to do. So we'll say T4 over T3 equals V4 over V3 to the power of K minus 1. Now, is V4 over V3, is that going to be 9? Is it going to be 1 over 9? Well, is V4 bigger or smaller than V3? So we're going to state 2, we're compressing, right? V3 is the same volume. It's a smaller volume as it's the smaller volume. So, oh, sorry, I inverted something here. This should be V3 over V. There we go. Sorry, it's V3 over V4. And V3 is the same volume as V2, so that's the smaller of the two volumes. So we know instead of 9, this is actually going to be 1 over 9. But again, if we want to isolate T4, we get T3 times 1 over 9 times K minus 1. Where K is 1.4. Now, in this case, we actually know T4. We're told that it's 800 Kelvin, and we're solving for T3. So if we do that, if we solve for T3, I'll just put a note here. If we solve for T3, we'll get T3 is equal to 1926.5. Oops, 0.5 Kelvin. Now that we know T3, like I was saying earlier, now we can sort of reuse this guy here to find P3. Going from state 2 to state 3, we can now do that. I'll do it actually up here. So I'll say P2 V2 over T2 equals P3 V3 over T3. Now again, we're trying to solve for P3, so if we isolate P3, we're going to get P2 V2, I'll say over T2, T3, P3, V3. Now the ratio going V2 and V3, the ratio is 1 because the volume hasn't changed, right? So we can cross that out. And now we're left with P3. Oh, sorry, I repeated that shouldn't be there. P3 equals P2 T3 over T2. Now P2 is known, we found it over here. T3 we found over here, and T2 we found earlier on over here. And if we substitute in the values, we get P3 equals 2167 times T3 over T2. So 1926.5 over 734.5. And that comes out to 5683.8 kilopascals. So we just found the pressure here. We already found the temperature there. So these are the highest pressures and temperatures in the entire cycle. And of course, they both occur simultaneously at state 3. But that's not all. We're asked to find the amount of heat added or transferred. So that means the heat transfer to, the heat transfer from. And we're also asked to find the thermal efficiency of the system. So I'm going to erase some stuff. Well, I'll make a new sheet here. So first thing we want to do is we want to look at the heat that was transferred from state 2 to 3. Now, of course, we know Q dot, well, not Q dot, we don't want the rate, we want the actual amount. So Q equals the mass of the fluid in the cylinder times the change in internal energy between the two states. right? And of course, because ideal gas law, we can say, sorry, mCv T3 minus T2. Well, we know T3, we know T2. CV we can get from the charts, it's 0.718. The only thing we don't know is M. So before we can really start calculating the amounts of energy added to the system, or done by the system, whatever, we have to figure out what the mass is. And we can do that from ideal gas law. So PV equals MRT. And we basically what we're going to do is we're going to choose any state we really want, any state, and we're going to put all the values we know for that state there and solve for M. So let's use state 1. So we have M equals PV over RT. Now we're told in the question, what was the volume? We're told in the question initially the volume is 600 cubic centimeters. But of course, we have to convert that into meters squared, which gives us 0.0006. So 0.0006 cubic meters. Pressure at state 1, 100 kilopascals. R for air is 0.287 kilojoules kilogram Kelvin. And the temperature, again, given in the problem, is 305. So all these values are given either in the problem or from the tables. And if you calculate this, you'll get a mass of 6.85 times 10 to the negative 4 kilograms. So we're going to use this mass to find the heat transferred to the system by plugging it in over here. So we know M, we just found that. CV, we know from the tables, it's 0.718 kilojoules per kilogram Kelvin. And T3 and T2, well, we found T3 and T2 just before. So they were 1926.5 and 734.5 respectively. So let's plug those in. 6.85 times 10 to the negative 4 times 0.718 times 1926.5, 734.5. And this gives us a value of 0.587 kilojoules. So this is the amount of heat transferred in the heat addition process. So this is, of course, transferred by burning fuel. Now, let me just check what we're asked exactly. We're asked to find the amount of heat transferred in kilojoules and the thermal efficiency. So they don't specify heat transfer as in to the system or from the system, so we can just find both to be safe. If we look at, if we want to find the heat rejected from the system, it's exactly the same thing. But instead of T3 minus T2, we're going to do T1 minus T4. And when we do T1 minus T4, a T1 is known from the T1 and T4 are actually both given in the problem statement. So if we just swap those values, we'll get, so this is, by the way, Q in and here Q out. So sorry, let me replace that. 6.85 times 10 to the negative 4, 0.718. And then we have 305 minus 800. And this gives us negative 0.2436 kilojoules. Now, obviously, this is a negative value, which is what we expect because this is a heat rejection. We're losing heat. Now, we want to find the thermal efficiency. And remember, thermal efficiency in any cycle, Brayton, Otto, Rankine, it's always what we're getting out versus what we have to give. to get that. So what we're getting out is our work net. What we're giving is our Q in. So is there a way we can find work net without doing this? Well, we could do this, or there's a much simpler way, which is recognizing that if you have a system and you're giving it a Q in, you're rejecting a Q out, and you're outputting some work. Well, by looking at the first law of thermodynamics, what goes in must come out. So Q in equals work net plus Q out. And that means that work net equals Q in minus Q out. And if we pop this over into here, we're going to get that the thermal efficiency equals Q in minus Q out over Q in, which if we simplify is equal to 1 minus Q out over Q in. And we found both of those values. So 1 minus 0.2436 over 0.587. And this gives us, let me just calculate it, 1 minus 0.2436 over 0.587. 58.5% thermal efficiency, 58.5%. That means that of all the chemical energy that we're supplying and turning into heat, of all the heat we're supplying, only about 60% of it is actually being used as work, and the other 40% is being wasted. Okay, so that's how we do the Otto cycle.